IGCSE Computer Science, Syllabus Statement 1.1.1a, recognize the use of binary numbers in computer systems. So, for this course, you need to know about binary. So that's one of the main aspects in this sort of the foundation. So, the basic building block of computers is binary. But what is binary? Well, binary is a number system. So everyone should be familiar with decimal, the decimal number system, which is our number counting system. So we have numbers 0 to 9, and then 10, 11, 12, and so on. Well, binary is like that, but it's binary, so it's base 2. Our counting system is what is known as base 10, but binary is base 2. So what that means is we know that our number counting system, when we start with one digit, and we get to 9, and we want to add 1 to that, and we want to go to the next value after that, we add another column to the left, we turn the 9 into a 0, and then we put a 1 on the left. That's pretty much how base 10 works. It's binary, it's like that, but 2. So there are only 2 possible values, which are 0 and 1 for each digit. Computer systems have millions of switches, which can be off or on, and this logically lends itself to binary. What this means is, if you think about your computer, which is in front of you right now, like it could be a phone, a laptop, or whatever, like it contains millions of tiny switches, which can be off or on. On meaning electricity passes through it. So when we say that it logically lends itself to binary, we say that 0 represents off and 1 represents on. So you can kind of see how binary would work with the system quite well. So it's like a light switch in your room. So like a 0 would be lights off, 1 would be lights on. So again, our number system is decimal base 10. So an example of a decimal number would be 36. But in the computer number system, binary, base 2, a binary number would look something like this. And in fact, this is the equivalent to, this binary value is the equivalent of the decimal value 36. And we'll get to converting binary and decimal values in the next video. So we have this thing here. To better understand how the decimal system works, each of these represents a sort of digit, column for a digit. So each column is a digit, really. So here we have 10 to the power of 0, which gives 1. 10 to the power of 1 is 10, and so on. It's basically 10 to the power of n, and it keeps going, left. As we go left, the n increments, so we get these. Now what this basically means is what we're actually going to do is get to this in the next video when we look at conversion, so it better makes sense. What makes better sense? Does better make sense? Does that make sense? But binary is this, but with 2 to the power of n. So you can see base 10 is 10 to the power of n, base 2, 2 to the power of n, and we get these decimal values here. So we're actually going to better understand this in the next video when we look at conversions. IGCSE Computer Science, Syllabus Statement 1.1.1b, convert positive decimal integers into binary and vice versa. So what we covered in the last video is what binary was, basically, and a bit of how it's used, although not that much. So this video will teach you how to convert decimal integers into binary and vice versa. So this is more math than theory, so just to let you know that. So just a recap of what we did cover in the last video, and don't worry if you haven't seen it, because I'm sure it's quite easy to catch up. as long as you know what binary actually is, then you know. So, just a reminder, our number system is decimal, which is base 10. So like a value of decimal would be 36, for example. Computer number system is binary, which is base 2. So a number would be something like this. And in decimal, since it's base 10, only 10 possible digits exist, which are the numbers 0 to 9. And for binary, it's only 2, which are 0 and 1. So just another recap of what we got to. So each column here would represent a decimal digit. So in this case, say 3, 6. 3 would be here, 6 would be here, and would be 36, and you'll see why in the next slide. But in binary, it's pretty much the same principle. So you could put this number into here, and well, you know. So yeah, let's get to that. So to better understand this, let's take the number 362. We plug it into this table here, so 362. So we get 3 times 100 plus 6 times 10 plus 2 times 1. So it would be 300 plus 60 plus 2, which would give you 362. So for binary, let's take this number here, for example. We have 1 in, well, under 8 and 1 under 4. So it would be 8 times 1 plus 4 times 1, which would give you 8 plus 4, which would give you 12. So that number here, the binary number, would be 12 in decimal. So let's try converting 36 into binary. So we get our table here, and this is one of 2 methods that I'm going to be showing you in this video. So first we check the number 36 against the leftmost number here. So 128 is higher than 36, so 0 would go under 128. Same with 64. So 64 is higher than 36, so 0 would go under 64. 32 is less than 36, so 1 would go under 32. And 36 minus 32 gives us 4, so now our number is 4. So technically, 36 has been used up by the 32, and then we have a remainder of 4. So we use the 4 to calculate, well, to check the next set. So 16 is higher than 4, so 0 would go under 16. Same with 8, 0 would go under 8. Now 4 equals 4, so 1 would go under 4. 4 minus 4 is 0. We put a 1 under the 4. But then 0 is less than 2 and 1, so zeros would go under them. So our binary number would be 0, 0, 1, 0, 0, 1, 0, 0. And just like decimal, the zeros in front of the first 1 can be ignored. So these can be ignored, and the number can be read as 1, 0, 0, 1, 0, 0. So let's try the second method, so using the same number to prove that it works. So this is the division by 2 method, so we get the remainder. Now we know that with the number 2, the remainder can only be 0 and 1. So let's do this. So 36 divided by 2 would give us 18 with a remainder of 0. 18 divided by 2 would give us 9 with a remainder of 0. 9 divided by 2 would give us 4, remainder 1. So 4 divided by 2 would give us 2, remainder 0. And 2 divided by 2 would give us 1, remainder 0. And 1 divided by 2 would finally give us 0, remainder 1. So what do we do with this? Well, you'll notice the remainders, as I said, can only be 0 and 1. So there's our binary value. We read it from bottom to top to get 1, 0, 0, 1, 0, 0. And if you want to, you can put zeros here. But that just proves that this method works as well. And you can choose between what method to use. They're both good. So let's try converting binary into decimal. So take this number here, for example, what you do is set out your sort of binary table here and plug the numbers in. So what you do is, well, you do same thing introduced to you in the beginning of this video. So it would be 128 times 1 plus 64 times 1 and so on, which would give you 202. It's the same thing with this. Plug in the values, find the parts which only have a 1 below them, which are these. 32 times 1 plus 8 times 1 plus 2 times 1 gives you 42. So what about if all the ones are filled and we want to represent a higher number? Because this would be 255. So what about something like 256? Well, remember that for base 2, it's 2 to the power of n, which means that we don't have to go up to only 2 to the power of 7. It can keep going. So 2 to the power of 8 would be 256. So we'd look at this number here, and 256 would then be a 1 put under it, and the zeros are the rest. And you can represent higher numbers than only 255. So if you want to represent, say, 1,000, then you could keep adding to the left hand side 2 to the power of n, and that's it. IGCSE Computer Science Syllabus Statement 1.1.1c. Show understanding of the concept of a byte and how the byte is used to measure memory size. So a binary digit is referred to as a bit. So like, remember binary digits like zeros or ones? If you put these two together, like the b from binary and the it from digit, we get bit. 8 bits are referred to as a byte. And a byte is the smallest unit of memory on a computer. Now you might be wondering, wouldn't a bit be the smallest unit of memory? Well, the thing is, a bit is, remember, a 0 or a 1, so that can't really store a lot of data. I mean, like, it's really small. Like, you can only store a 1 or a 0. Like, so just think about that. And, like, even a byte is too small to store a significant amount of data, which is why memory size is measured in the following multiples. So, like, if you have a text file or a movie, like most movie files, like MP4 files, are pretty, like, not so big, but they're like a 20-minute episode, 1080p would probably be like I don't know. I can't really estimate. It's okay. It's pretty large, and it's usually measured in megabytes, which you're gonna find out what they are in a minute if you don't know what they are. So like, there's kilobyte, which is 2 to the power of 10 bytes, so that's 1024. There's a megabyte, which is 2 to the power of 20 bytes, and that's 1,048,576 bytes. So, like, that's 1 megabyte in bytes. So, like, as I was saying with the movie, like, a movie would... Okay, let's take a regular sized MP4 file, and let's say it's, say 100 megabytes. So, like, that would be, like, a normal, kind of short-ish movie file size, and that's pretty big. Like, so you can see why a byte is too small to store, like, anything significant. And then there's gigabyte, which is 2 to the power of 30, which is also a really large number of bytes. Then there's the terabyte, 2 to the power of 40. This is, again, an even larger number. There's the petabyte, 2 to the power of 50, and again, they just keep getting larger. Exabytes, zettabytes, yottabytes, and they're pretty huge. Most computers nowadays should be like a terabyte or two, I guess. Like, most old computers should be like 300 to 500 gigabytes, but eh. Like I'm talking about laptops, not actual computers. It's like I have a laptop and I don't actually have. I didn't have a desktop for like since a few years back, but anyway, there are also bit multiples. So like along with kilobyte, megabyte, gigabyte, there's also kilobit, which is 2 to the power of 10 bits, megabits, and so on. So, bit multiples versus byte multiples. So, we remember that 1 byte is 8 bits. So that would mean that 1 kilobyte would be 8 kilobits, 1 megabyte would be 8 megabits, and so on. So you might get a question in the exam, like the upload speed on the internet is 32 megabits per second. How long would it take to upload a 40 megabyte file? So first you convert 32 megabits into megabytes. So remember that 1 megabyte is 8 megabits. So it would be 32 divided by 8, which would give you 4. So 32 megabits is 4 megabytes. So that would give us 4 megabytes per second, because it's megabits per second here, 32 megabits per second, so that would become 4 megabytes per second. And we have a 40 megabyte file, so easy, 40 divided by 4 gives us 10, so 10 seconds to transfer. IGCSE Computer Science Syllabus Statement 1.1.1d, use binary in computer registers for a given application. So, when computers or microprocessors are used to control devices, they make use of registers. A register is a small amount of available storage used for a specific purpose and with quick access time. So basically, a group of bits. So, like, if you remember binary, we know that from the last video, data is stored using bits, bytes, and kilobytes, megabytes, and so on. Remember that it's all a bunch of ones or zeros, a bunch of bits. So a register is basically a group of bits. So it's often depicted as something like this. So we'll look into it right now. So like, you might get a question on the exam saying an 8-bit register is used to control a specific device, such as a washing machine in this instance. So you might get something like this. So it'll tell you which bit here represents what function it performs. So basically how it's used is, well, probably say each of these squares here, or columns, is given a bit of 0 or 1. So for example, this, as you can see, there's a 1 here, 0 here, 1 here, 0 here, so on. So here, if you remember in binary, 1 is on or true, and 0 is off or false. And the true and false thing, this whole thing with binary is called Boolean, which I don't think you need to know for the course, but, well, I mean, you're going to get something called Boolean algebra, but I think that's as far as you go. But I'm not, like, actually I can't think of anything off the top of my head where else you would use it besides that. Okay, so in this case, if machine on is true, because it has a value of 1 here. Valve on is true, because it has a value of 1. Agitator off is true, because it has a value of 1. And pump is off, because it has a value of 1. So the rest are false, as they have zeros. So therefore, this is the effect that it would have on the washing machine if the register contained these bits. So what if the register contained these bits? So machine on is true, valve off is true, agitator on is true, and pump off is true. The rest, of course, are false. So that's the effect that it would have. So you might also get a question saying, what would the register contain if only the machine was on and the agitator was on? So what we do is we look at the question and we see machine on is true because it's on. and agitator on is true because it's on. So the rest are off. So basically, well, let's look at machine. So machine on is true and machine off is false. Valve on is false, which means that valve off should be true. And agitator on is true. That means agitator off is false. And pump on should be false and pump off should be true. So what would the register contain if only the machine was on and the pump was on? So again, we look at the question. Machine on is true and pump on is true. The rest are off. So machine on is true, machine off is false. Valve on is false, valve off is true. Agitator on is false, agitator off is true. And pump on is true and pump off is false.